Swayam Prabha. Digital India. Educated India.
So last class I have discussed about different ground motion parameters. I have discussed about the amplitude parameters, and then I started the frequency parameters. In amplitude parameters, I have discussed about the acceleration, velocity and displacement. And here in the frequency content parameter, I have discussed the Fourier spectra, and I have derived the equation of that Fourier series, and where you can see the plot between Cn or the Fourier amplitude versus frequency or time period, that is called Fourier spectra. Now today I will discuss more about frequency content parameter and then duration of time if times permit. Now you can see that this I have already discussed, that is the frequency content parameters. The first one is the Fourier spectra. So this is the plot between Fourier amplitude and frequency or time period is known as Fourier amplitude spectra. Okay, so and we have already discussed what is the meaning of narrow spectrum or the broad spectrum, and we have derived the equations also. Now one more parameter, that is the corner frequency and cutoff frequency. What is corner frequency and what is cutoff frequency? That if I plot that Fourier spectrum. So here plot that Fourier spectrum in a log scale, that this is my Fourier amplitude, so this is in log scale, and this is the frequency, that is also in log scale. That is also in log scale. Okay. Now if I plot that, then I will get at portion is uniform. Okay. So that starting of that part, this is called FC, corner frequency, and the end is called the F max or the cutoff frequency. Okay. So that means the corner frequency is inversely proportional to the cube root of the seismic moment. Okay. And large, so here it indicates that large earthquakes produce great low frequency motion as compared to the smaller earthquake. Okay, so that means we know that the Fourier amplitude spectrum of actual earthquake motion, if this is for smooth acceleration, if we can are smooth. Okay, so that if the Fourier amplitude spectra of actual earthquake motion are smooth, then the largest Fourier acceleration amplitude is observed over an intermediate range of frequency. So you can see that the largest Fourier amplitude is observed. So here if I plot them in this, it is in log scale, that is the Fourier amplitude in log scale and the frequency is also in the log scale, then I can see that the largest Fourier amplitude is observed over an intermediate range of frequency. You can see intermediate range of frequency, and so that indicates that the large earthquakes produce greater low frequency motion as compared to the smaller earthquake. Clear? And this is your corner frequency and this one is the F max, is the cutoff frequency, and as I have already discussed, the corner frequency is inversely proportional to the cube root of the seismic moment. Now next parameter, that is the power spectra. Okay. So power spectra can be used to describe the frequency content of a ground motion. Okay, like the other spectrum, it is used to estimate the statistical properties of a ground motion or characterizing the earthquake as a random process. Okay. So next one is the response spectra, which is very important. Okay, the definition of the response spectra is the response spectra describe the maximum response of a single degree of freedom system for a particular motion, and which is as a function of natural frequency or natural period and damping ratio of the single degree of freedom system. So that means it is a function of only natural frequency or natural period and damping ratio, and so that means it is described by the maximum response of a single degree of freedom system for a particular motion. So it is the maximum response. Okay. So response spectra can be divided into three portions, that is the acceleration control, it is the high frequency zone, then the velocity control, this is the intermediate frequency, and the displacement control, this is the low frequency. In the last class I have discussed that high frequency zone, your acceleration is more sensitive, then for the intermediate zone is velocity, and the low frequency zone displacement. Okay, so that means it is divided into three portions: acceleration control, velocity control, and the displacement control. Now here we are talking about response of a or maximum response of a single degree of freedom system for a particular motion. So let's discuss about that, what are the different types of motion and then what are the different conditions. So first one, when we are discussing about the response of a linear single degree of freedom system, because the response spectrum means it is the maximum response of a single degree of freedom system for a particular motion. So now we will discuss what are the response of a linear single degree of freedom system under different conditions. Okay, and from there you will get an idea how that maximum response can be calculated, and then finally the response spectra can be obtained. Okay. So now what is the response of a linear single degree of freedom system? First we can say what is the force vibration and free vibration. Force vibration means when the mass is subjected to external loading which can be periodic or non-periodic. So that means I have already discussed I have given you the equation of motion. So and there is a mass spring dashpot system, and where if that mass is subjected to external load, then it is called the free force vibration. Now what is free vibration? When the vibration occurs in the absence of any external loading or base shaking due to the release of mass from some initial displacement or after the end of some transient force vibration. That means it vibrates, or when the vibration occurs absence of any external loading. So that is called free vibration, and when it occurs it is been discussed. Now what are the different conditions? So that we can say that there is a damper. So if the free vibration but undamped condition, when the damping is 0, because we have seen the basic equation, It is mass into acceleration plus your damping into the velocity plus stiffness into the displacement. That is equal to external loading. Now, if external loading is 0, there is no, that is the free vibration, but if undamped, when damped, C value is also 0. So, that means in this case your C value is 0 and QT value is also 0. So, you know that this is my equation, that M double dot plus Cu, or you can write M double dot function of T also, plus K into U, that is equal to Qt. Okay. So, that means here if Qt is equal to 0, because it is a free vibration, and C is equal to 0 undamped condition, then that is one condition. What is damping? Damping is mentioned here, dissipation of energy in soil or structure by the means of friction, heat generation or plastic yield is called the damping. If this is the undamped system, then C will be 0. Next condition is damped free vibration, when C is not 0 but Qt is equal to 0. Third one is the undamped force vibration, when C is equal to 0 but Qt is not equal to 0. Then fourth one is the damped force vibration, when C is not equal to 0, Q is also not equal to 0, Qt. Okay. So, this loading is first two cases, that means third and fourth cases loading is harmonic loading, but in the fifth cases when the mass is subjected to any periodic loading, okay, then how we can got the response. And the last one is the step loading. Okay. So, let us one by one I will discuss about the response of this all these conditions. So, first one that is discuss about the first case, that is my undamped free vibration. Okay, so the equation of motion will be what? M double dot plus K U, that will be equal to 0, because C is 0 and Qt is equal to 0. Now, I am not going to in detail about the derivation. I am giving you the final response or the solution. So, if you want to get that complete derivation, then you can go through some soil dynamic course or dynamic course where you will get all the detailed derivation. But in this course, the scope of the detailed derivation is limited, because here I am just giving you the idea of that, what is the response and how we will get the maximum response, and from there I will get your response spectrum. So, now the solution or the response that will be that U, T or U is the displacement, that is you will be U0 divided by omega 0 sine omega 0 t plus U0 cos omega 0 t. That is the equation. Now, what is omega 0? Now, where omega 0 is the undamped natural circular frequency. It is undamped natural circular frequency. How you can get that value? That is equal to root over K by M. So, K is the stiffness and M is the that constant rigid mass. Now, from here I will get the natural frequency . How will get the natural frequency? F0, that will be omega 0 by 2 pi, because we know that time period or t is equal to 2 pi by omega. So frequency will be omega by 2 pi. So this will be omega 0 by 2 pi. So this is 1 by 2 pi, omega 0 will be root over k by m. So natural frequency I will get by using these expression, because omega 0 is equal to root over k by m. Now similarly I can write that natural period of vibration so that is equal to that T0 will be 1 by F0. So that will be 2 pi by omega 0. So that will be 2 pi then root over m by k. Okay, and that I have already discussed in my previous lectures, that how we will get the T0, because it is the time required to complete one cycle. So that is 2 pi and divided by the velocity or angular frequency, natural angular frequency, or the speed, angular speed. Okay, so now here what is that U0? U0 is the initial displacement. So these two are the initial conditions. So U0 dot is the initial velocity. Okay. So this equation, that UT equation, I can write, because I have already discussed that if we have a equation in this form, that harmonic loading we are talking about, so that we discuss about that in trigonometric form, that if it is A cos omega t plus B sin omega t, then this one I can write by A sin omega t plus phi, where A will be equal to A square plus B square and phi will be equal to tan inverse A by B. The same thing I will do here. Like if I convert this one, then I can write this is A sin omega 0 t plus phi. Okay, so A will be root over A square and B square. So this is your A and B here. So I will write this is A square will be your, this is A, this is B, because this is your cos omega 0 t. So this will be A square plus U0 plus omega 0, that is B square, and phi will be equal to tan inverse A by B. A is equal to U0 and B is equal to U0 by omega 0. So that will be here. Okay. So from here, what will be the maximum U? So U maximum response or maximum value of displacement. So maximum will be, so this, if I take the absolute value, then sin omega 0 plus phi can be, maximum value can be 1 or it can be minus 1 also. So I am just taking the absolute value. So that means the maximum value will be here A. So that is the maximum displacement of this particular undamped free vibration system. So we will get this, how we will get the response of a particular case. So now if I draw this your displacement versus time plot. So if this is time, if this is U or UT, then I can write there is the initial U0. So that will start from here, then it will go up like this. So what is this value? This is the initial velocity, and the slope of that will give you u dot 0. Okay, and here this is the time period. So natural time period t0 will be what? T0 will be 2 pi omega 0. Clear? So these u0 and u0 dot, these are the initial condition. I mean at u0 equal, that is when t equal to 0, and this velocity u dot 0 when t equal to 0. Okay. So now if I go to the next case, that is our case 2, that is damped free vibration. Okay, so my equation of motion will be that will be that m u double dot plus, here it is damped case, so damping will be there, plus ku, that will be 0 because it is also free vibration, no external loading. Now solution of this equation or response, that will be equal to u or ut, that is equal to e to the power minus damping ratio into omega 0 t, that within bracket u0 dot plus damping ratio omega 0 u 0 divided by omega d into sine omega dt plus u0 cos omega dt. Okay. Now here where omega d is equal to damped natural frequency, circular frequency. Initially it was omega 0 undamped natural circular frequency. Here it is damped natural circular frequency. How I will get this value? That is equal to omega 0 root over 1 by damping ratio square. So you know that this is your damping ratio. So what is damping ratio? That is your actually C by C, Cc. What is C? C is the damping coefficient divided by critical damping coefficient. Okay. Now this Cc, critical damping coefficient, we can determine by 2 root Km. Okay. Now if your damping ratio is less than 100%, that means my C is greater than Cc, then the system is called the underdamped system. Okay. And if it is equal to 100%, then C is equal to Cc, then the system is called critically damped system. And if it is greater than 100%, that means C greater than Cc, then it is called overdamped system. but the solution that is given or the response that is given, it is for under damped system, because most of these geotechnical earthquake or earthquake engineering problems are under damped system. Okay. So here if I draw the graph or the plot, that is displacement versus time. So this is time and this one is ut. So here also I will get some initial velocity. Then actually will this there will be a decay or decrease. Okay, so you will get this type of So you will get, this is from initial value, so like this. Okay, so this is my u0 initial value and the slope that will give you u0 dot. Okay, and obviously this one will give you, this value will be 2 pi by omega d, because it is damped system. Okay. So now there is a, this is the decay, the decay is logarithmic decay is there. So those is there. So now this decay, logarithmic decay we can calculate, because this decay is there. Decrement delta. Okay, so delta how I calculate? Delta will be 2 pi damping ratio 1 divided by damping ratio. Now after rearranging this equation, what I will get, that my damping ratio is equal to delta divided by root over 4 pi square plus delta square. Now if delta is small, then I can get the damping ratio is equal to delta by 2 pi. If delta is small, this part I can write that is equal to, if delta is small, I can write 4 pi square plus delta square, because delta is small and it is delta square. Then that will be equal to 4 pi square. Now within root of 4 pi square, it will be 2 pi, so it will be delta by 2 pi. So thus the damping ratio of a single degree of freedom system can be determined by performing a free vibration test with a u0 and acceleration equal to 0. So that means the damping ratio of an single degree of freedom system can be determined by performing a free vibration test with a u0 and taking u0 dot is equal to 0. That means velocity, initial velocity is 0, but there will be some initial displacement. So this way we can determine that damping ratio. Okay, if I know this decay, okay, by this expression, if I know the decay, then by doing this by performing a free vibration test with initial velocity and keeping with an initial displacement. By keeping initial velocity 0, we can determine the damping ratio. Okay. So, this is the two cases I have discussed, that is the two cases. First one is the undamped free vibration, second one is the damped free vibration, and I will get the response. Okay. And then the next class I will discuss few more conditions, and I will show you how we can get the response of the of different cases, and then from here I will get the response picture. Thank you.